so they will be continuing our study of Extension 1 Mathematics, and we'll be doing that with the study of vectors, which is a new topic for some of you, particularly those of you who aren't doing physics at the same time as this course. But for those of you that are doing physics, this will all just be reviewed. So, what are vectors? Well, there are two kinds of quantities we can look at. We can look at a scalar quantity, which is something with a magnitude or a size, but no direction. So if I say, for example, that person X traveled 5 meters, then I've just specified a magnitude. So that is then a scalar because I haven't specified what direction they traveled. But if I have a vector, what I'm going to do is I'm going to then specify a magnitude and direction. So if I say person X travels 5 meters east, then that means that that is a vector because I've specified the direction, which is east, and the magnitude, which is 5 meters distant. So vectors are actually really useful because we can use them to represent situations in really clear, with very clear diagrams. So if we look at these examples, we want to draw a vector to show a train traveling 150 kilometers on a bearing of 210 degrees. So if we look at this, if we remember our true bearings, then we can look at our north line. And what we're going to want to do is we're going to travel 210 degrees. So we're going to want to go from our north line and go all the way around in the clockwise direction to 180, which is in the direct opposite direction, and then an extra 30 degrees. So that should be about there. So now we can draw our vector here and 210 degrees. Now this represents the direction of the vector, so we're all good on the direction part, but we also need to specify the size. So what I'm going to do is I'm just going to write 150 kilometers attached to that vector. So that then specifies that it's a 150 kilometer vector traveling in 210 degrees from north. And it's whatever starting point you have. You might specify a building or a town or basically wherever you want. That's essentially the beauty of vectors, and that we don't have to know too much about the situation. It's sort of a general rule that we can use to represent things with magnitude and direction. So now if we want to look at a person walking 3.5 kilometers due east, rather than using bearings, we're using compass points. So we're going to say, this is north again. So east is going to be here. You should all know this. That's 90 degrees. So again, this has specified the direction of the vector we want. And if we want the magnitude, we go 3.5 kilometers. So that's it. So we've essentially just used the theory of vectors to very easily represent both scenarios just using an arrow. And realistically, in a situation, you don't need the north lines, but because here, it's essentially no other way of us saying that this is directly east or this is 210 degrees on a bearing. So we're going to include them here. So that this just specifies the direction. Anyway, let's look at some other theory relating to vectors. And let's look here. So if we're looking at equal vectors, it's really important that the two vectors are equal if they've got the same magnitude and direction. So if I have two vectors, and let's say I have this vector here and this vector here. So let's assume that they're parallel and they're going in the same direction. And this vector is 5 meters long, whereas this vector is 10 meters long. So note that these aren't the same vectors because they're different lengths. But if I were to then shorten this to 5 meters, but place it down, then these still aren't going to be the same vectors. Even though they are the same length, and you're used to things that are the same length being the same, they are different because they're pointing in different directions. So they're going to have to be parallel and they're going to have to be the same length to be the same vector. But importantly, this vector here, AB, and this vector here, XY, these are the same even though they're not in the same location. So as long as they're the same magnitude and direction, they don't have to be in the same place to be the same. Because this one's over here on the left and this one's over here on the right. They're clearly not in the same place, but they are still the same vector. So now let's move on to some more concepts regarding classifying vectors. And let's look at parallel vectors. So I just mentioned that when two vectors have the same direction, they are parallel. So, sorry, I went one too far. All right. So, when we have parallel vectors, we say that they're in the same or like direction. And when we have opposites, they are unlike or anti-parallel. So they're in the opposite direction. So note that the reason we specify this is because even though it's in the opposite direction, with vectors, there's a few things we can do if they're not quite parallel, but they're pointing in the opposite direction. So here, these both are parallel, but this one is anti-parallel or unlike parallel to the other two vectors. And there's a really easy way of representing this relationship in vectors as well. And again, these are some of the reasons why we use vectors so much, because they allow us to do a lot of really simple things to represent concepts. So essentially, this is what I was talking about, negative vectors. All we have to do, if we have a vector A, and it's going in this direction, all we have to do to get an anti-parallel or an opposite pointing vector with the same magnitude is to just put a negative sign out the front of that vector and when we start looking at coordinates, we'll just be essentially making all the points negative. So what we'll be doing here is we have our vector A, and when we make a negative in front of that, we get the vector pointing in the opposite direction. But note that they're still going to be the same lengths. We're not affecting the size of either of these vectors. We're affecting the direction. But again, because we've affected either the size or direction, in this case direction, they are not the same vectors. That's really important. A vector is not the same as the negative version of that vector. That's really important. But it's also really useful to just be able to make this negative sign and then change the vector to be anti-parallel. Now, if we're looking at unit vectors, these also are mostly to do with size. These are mostly to do with direction again, rather than size, because a unit vector is, as this suggests, a vector with magnitude 1. So why would we care about a vector of magnitude 1? Are we looking for size and magnitude? And if it's just a magnitude of 1, that doesn't really do much. Well, just like how when we put a negative sign at the front, we can change the vector to be anti-parallel, so we're essentially making it the complete opposite direction. We can use unit vectors to change direction in other ways. So if we don't want to flip it a whole 180 degrees, and let's say we just want to turn it, say, 30 degrees, we can use unit vectors to do that using processes that we'll talk about later in other videos. But essentially, unit vectors are a really important concept because we can use them to just affect the direction of a vector and not its size. So now let's look at some types of vectors. So we want to describe the relationship between each pair of vectors. So with A and C, so if we look at A, it's pointing in this direction. And if we look at C, then we'll see that these are actually the same length, 8, but they're pointing in opposite directions. So they're going to be unlike parallel. B, D, and I. So we look at D and we look at I. So D and I are pointing in the same direction, so they are parallel, but they're not the same vector because I is 1/5 the size of D. For C, F and G, so if we look at F and we look at G, then they're pointing in the same direction, both vertically, and they're also the same magnitude, 5. So these are actually going to be the same vector. And for D, B and E, B and E, which is over here. So they're parallel because they're going in the same direction, vertical, but again, they're not the same vector because B is 1/8 of E. We want to look at D and H, so D and H. So they're parallel again, but they're pointing in they're the different size. So one's 5 units long and the other's 8 units long. So they're parallel, that's their relationship. F, I, and J. So if we look at I, it's going to be 1, and J is also 1, and they're not pointing in the same direction, but it looks awfully similar. It seems like they're pointing in opposite directions. So they're not like parallel, they're unlike parallel. All right. I hope this was a useful introduction to vectors, just going over some concepts regarding classifications of relationships and just generally what a vector is. Anyway, I'll see you guys in the next video.